Good news, pizza lovers. It's time to make something. Step one, as always, is make your bed. My bed's made. Is yours? Okay, what we're going to make is an LED. The light's up, and the brightness is going to be controlled by a potentiometer. Here's a breadboard, microprocessor, potentiometer, LED. See the pins? One of them's longer than the other. The longer one is the positive side, and the shorter one is the ground side. So I've grounded this through the microprocessor. Here's the potentiometer, not wired up yet. The microprocessor is the Seed Studio Zhao. They make a few of them. It's the ESP32C3. It has onboard Wi-Fi and Bluetooth. This is the Wi-Fi antenna. Let's look at the data sheet for this one. So here we have a pinout, and I can see that there are pin numbers and they have different names. I think that the blue ones are what they're called in the Arduino IDE. So we're going to look and see what we have to do to program this thing with Arduino. Yep, here we go. 0, 1, 2, 3 through 10. Alright, so we're going to get the Arduino IDE, and they have some setup instructions for how to install support for this microprocessor. So we're going to follow those steps and download the support package from Seed Studio for this microprocessor. Now the potentiometer is going to be connected only to the microprocessor. We could wire this circuit without a microprocessor, just with the potentiometer and some resistors. We would actually have to do something, because this potentiometer goes from 0 to 10,000 ohms. So what we're going to need to do is, instead of having the potentiometer control the resistance that's prior to the LED in the circuit, what we're going to do instead is we're going to have the microprocessor read an analog voltage signal, and then it's going to send separately a voltage signal of some synthesized voltage by using an analog output signal. We might have to use a PWM, I'm not sure yet. PWM is pulse width modulation. It's a square wave, so if you want to send full voltage, you just send, the max PWM range is 255. It's an 8-bit system, and so if you just send full squares with no space between them, then you're going to get basically full voltage of the system. But if you send thin waves with a lot of space between them, then it's going to average out to be a lower voltage, and the LED isn't going to be as bright. It happens enough times a second that it can simulate a leveled voltage. What we may have to do is some calibration, and we may have to see how this potentiometer works. It's got a little dial here that you twist. I might have to get out my electronic screwdrivers to deal with that. But the first thing is we're going to get the voltmeter and figure out the pinout for this LED. For the potentiometer. Well, I realized I gave my spare multimeter to a coworker, and I threw away my spare multimeter because I thought it was ridiculous to have that many, and now I don't have one. But it turns out that the pins on a potentiometer are standard 1, 2, and 3, and the information about what each of them is for is readily available. So here on the potentiometer we have a 1, 2, and 3. If you look closely. So the way a potentiometer works is you have a segment of resistive material. You have power and ground flowing along the whole length, and then the middle one basically is like a moving lead. So you're going to get more or less resistance based on where that lead is at along the length of the resistive material. That's how a potentiometer works. It's a variable resistance device. This one uses a knob. Many of them are a slider. A slider and a knob are the two basic ones. Usually the knob is like for fingers, but this one is very tiny. It's for a breadboard, and so it has a little screwdriver slot. So I'm going to the wires and get, you know what, let's actually run, what I'm going to do here is I'm going to bring ground from the microcontroller to this power rail and ground rail, and that way I won't have to stick ground leads here on the breadboard row. We'll just put this ground here for the LED. This kit, looks like this kit only has 2 black wires, so I'm going to use green. Green is often also used for ground. Okay, so we're going to have 1, 2, and 3 going down the row. Here's the final breadboarded system. The orange wire right in front is on analog 1 and goes to the middle pin of the potentiometer. The red wire on pin 1 of the potentiometer goes to the microcontroller's 3-volt output, and then ground for the potentiometer goes to the microcontroller's ground output, as well as on that same row, ground for the LED. And then on digital pin 10 is this red wire here, which powers the LED with a, I don't know, something like 200 ohm resistor. So that's the whole thing there. You got power and ground for the potentiometer and the LED, and then signal wire for the variable resistance of the potentiometer, and then a resistor so the LED won't blow up. It's time to do some math. We went kind of quickly over PWM and analog output and analog input and the LED resistor, so let's take a closer look at that now. So on the chip here, we've got a few, I think there are 4 of them, analog input.
and that is going to be sensitive to anywhere between 0 and 3.3 volts, and it's going to map that onto a number between 0 and, there's different resolutions, so you'll hear about like a 10-bit analog to digital converter or a 12-bit. This one is a 12-bit, so that means that we're going to get anywhere between 0 and 2 to the 12 minus 1, which is 4095. A 10-bit would be on the interval of 0 to 2 to the 10 minus 1, which is 1023. And so what that really represents is, the smallest indivisible unit of digital information is the bit, which is either 0 or 1. Byte is just 8 of those. Zero or 1, 8 of them. Okay, so we're going to have 12 bits for this analog to digital converter. So we're going to have the wire on that pin is going to have 0 to 3.3 volts active on it. And in the software, that's going to be read through the analog to digital converter, and we can call a function that's going to read that pin, and it's going to return a number, and the number is going to be anywhere from 0 to 4095. So that's what we're working with on the analog input. Now it's very common, and in this case I've experimented and it's true, there's often a dead band. So if the full domain is in fact 0 to 4095, this one is really only going to actually go up to about 3800, and it's only going to reliably go down to about 300. So in the software, we're going to act like the range is 300 to 3800, and so anything below 300 will be considered our 0 point, so I'll call that 0 prime, and then 3800 is going to be our max. So we're going to take values on this range and we're going to map them, and now we can talk about PWM. So from 300 to 3800, we're going to map onto the PWM range. This is the analog to digital converter, let's call it input, and we're going to map this onto a pulse width modulated signal from 0 to 255. PWM always uses 0 to 255, so 300 or less on the analog input pin will be mapped to 0, and then we're going to scale this interval from 0 to 255. So 3800 or greater will be 255, which is the max value. Okay, and so one way to think about PWM is like, let's call this time, and as time goes by, we'll have a PWM signal. Well, whenever it's sending, it's going to be sending the operating voltage of the microcontroller. That'll usually be 3.3 or 5 volts. So if we have a value like 255, we're going to get a very full square wave like this with a small interval between it. Oops. And so let's call that 255, and then let's say we have one that's at like 100. This is time. This one's going to be more like this. It's going to be kind of in the middle. And so then if we had like 0, that would be just a flat line. Okay, so how I think about this is like, for the LED, we're not going to be getting 3.3 volts, or here, like when the voltage is sent, it's at the logic level of 3.3 volts. But the way to think about this is like, imagine if these areas were like ice cubes or ice columns, and you melted them so that they had to fill in all of this area. It would just be one even level. So if you melted this, it would fall into an average value of like here, maybe a little higher. Say you create a scale 0 to 255 and you take the water level right here, you're going to find that on a scale of 0 to 255, it's 100. So like 40%, right? Because we call this 250 approximately, and 100 would be 40% of 255. Because it's 2 out of 5 50s, right? So that's how PWM works. It uses this like variable width square wave where the rising edge of this block, and that's actually what it's called, the rising edge, and this is the falling edge. So if you have a digital input signal that represents like a sensor input, like a button push, that will also be a square wave like this that will have a rising edge and a falling edge. And you can set processor interrupts to detect either edge sometimes. So the rising edge is going to be at a regular interval, and then the falling edge will be delayed after that based on the signal that the hardware PWM generator gets. The closer to 255 it is, the later the falling edge will be in this interval. The closer to 0 it is, the closer to the beginning it will be. So that's PWM. And there's a specialized hardware on the microcontroller. We give it a number, and then it generates this signal for us. So we just, in Arduino, it's pretty easy. We just call this analog write function, and we tell it which pin, and then we tell it which value. And off we go. Okay, now let's look at how to keep the LED from blowing up when we supply power to it. Well, an LED usually draws about 20 milliamps. And that's the value that I'm going to use for this one. I don't know for sure, the manufacturer didn't tell me, but that's a safe guess. So 20 milliamps is 0.02 amps, and we can use Ohm's law to figure out what kind of resistance we need in order not to blow up the LED. We know that the voltage of the system is 3.3 volts. And so we know that the current is 0.02 amps, and then we have resistance. So by dividing, we can find the resistance at 3.3 divided by 0.02. And we find that to be 165 ohms. Well, my resistor kit has one at 150 and one at 180. So I went with 180 just to be on the safe side. And so that's what we have there.
Alright, so here we have the Arduino IDE, and I am installing, as you can see in the bottom corner, the support package for the Seed Studio Xiao, which comes from Espressif, is the manufacturer that creates the ESP32 chip series. And just for transparency's sake, I'll tell you that I've written all this code already, and it looks like it's going to take a while to install the board support, but as I was saying, I've written the code for this project already because there's always some debugging, and as you go through that you have to rebuild the code each time, and we don't want to wait for all that during this presentation. So here we have the setup and loop functions that come from the Arduino framework, and setup will run once at the beginning, and then we'll call loop over and over until power is removed. So first thing we're going to do is set, we want analog 1 to be an input that's going to read a voltage between 0 and 3.3 volts. That's the operating voltage of the chip, and it's going to give us a number whenever we do that. Pin 10 is going to be the one we just chose arbitrarily to use to power the LED. And since it's when you have a large project, you may have a lot of I/O pins, and you don't want to refer to those by number in your code, because if you have to reassign one of your pins for some reason, you only want to have to change that in one place. So you refer to it by an alias or a macro, it's called in C. And we're going to have potentiometer pin be A1 and LED pin be 10. And so one reason why you might want to change your pins is, say you're using one for a general purpose input output, like reading a button input or powering an LED, for instance, and then you want to add some type of connectivity to your project using like serial peripheral interface, SPI, or I2C is another one. Those peripherals are usually only available on specific pins, so you might have used one of those just as a general purpose I/O. When you need actually now to reassign it, you can use any other pin for a GPIO, but your specialized hardware functions are only available on certain pins. So you might want to rename a pin for a reason like that. So, okay, another thing we're going to do in our setup is begin serial communication, and then each loop we're going to read from the potentiometer. We're going to call the analog read function to read the voltage on the potentiometer pin, and then we're going to transform that data somehow, and then we're going to power the LED according to the voltage that we read. So what we want to do is to scale the analog input from the range of 300 to 3000. So whatever value it is on the scale of 300 to 3000, we want that same value proportionally scaled onto 0 to 255, because our 12-bit analog digital converter is going to be between 0 and 4095, which is 2 to the 12 minus 1, 12 bits. But we found that just by experimenting, by doing a serial dot print line of the potentiometer reading variable, that this potentiometer will only go down to about a count of 300, which is the value we get from the analog read function. So what I did initially was serial.println of potentiometer reading, and that was it. and then I twisted the potentiometer knob all the way down, and it went as low as 300. And I twisted it all the way up, and it went as high as about 3,000. So really the range ought to be between 0 and 4,095, but in practice we didn't get that. So we're calling it 300 to 3,000. And now we're going to do some math here to scale that range, whatever your value is on that range, onto the other interval of 0 to 255. So we'll create a general purpose function to do that, and I have no shame in borrowing this function from Stack Overflow, because when I was in high school we did this exact same thing. When we had 2 joysticks to implement skid steering on our robot, and because the robot was 120 pounds and took off pretty quickly, we wanted to put a deadband around the neutral position of the joystick, because the microcontroller reading the joystick position there would be sometimes what's called drift, which means that even though nobody's touching the joystick, the value that's read sometimes changes. So we wanted to protect we wanted to protect our team members from the robot just taking off. So we put a deadband around the neutral position of the joystick so that you would have to move it, physically with your hand. It wouldn't just suffer from drift symptoms and start moving. That would be dangerous. So, and, we also put it on jack stands a lot of times too, but this was a safety feature. And so we also wanted to implement a quadratic scale of the acceleration and reverse as well. So we rescaled onto a quadratic interval. So this math is it's faster for me to just Google map a value from one range to another than to rethink it. But I have nothing to prove. I've done it before. So there's our scale function. And now what we're going to do is we're going to check to see. We'll start with a value of 0, so writing no voltage to the LED, and we're going to check, is this value greater than, if the value is greater than, so let's define these constants, the minimum and maximum. Let's give it a less misleading name here than pot max. That sounds like the finale of the Harold and Kumar series, or Bill and Ted or something. So if the value that we read is greater than the max value that we want to set our scale at, then we're just going to max out the PWM. And then we're only also going to change the value from 0 if the value is greater than the minimum, which is 300. So if the value is outside of the range, it's going to just pull to the min or the max PWM value. If it's in the middle, then we're going to use this scale function, and we're just going to put in the appropriate values here according to our function parameters. Put in those arguments. 0 and 255 we can just hard code in because those are part of PWM. It's just an 8-bit. So then we are going to call analog write, which will generate a PWM. It's called analog write, and it doesn't write a true analog signal on this board, although there are some Arduino boards that have true digital to analog converters. This board does not, and so it's going to generate a PWM, which will be functionally equivalent for our purposes. You won't be able to look at the LED and know that it's receiving a square wave instead of a steady voltage. Oh yeah, here's another thing that I like to do for debugging purposes is to print out the pre-transformation and post-transformation values, which would be the variable potentiometer reading and the variable PWM for LED. And the way we're going to do this is we're going to use a printf format string with a 4-digit decimal number of spaces, just for visual separation, just so it's easier to visually parse, and then a 3-digit decimal number. And the reason that I use the leading zeros in the case that the number is, so if the first number is less than 1,000 or less than 100, it would normally be less digits, but I like to pad the number with zeros so that it's always the same, so that if that value is changing a lot, your output is going to be a consistent number of columns, and it's just easier to keep track of as you're scanning the numbers flying by on the terminal. Because printing this every loop is gonna be going pretty fast, so what we want to do is to have that output a consistent number of columns, easier to read. So we're gonna sprintf, that string is gonna take these two arguments, potentiometer reading and PWM for LED, put those in where the placeholders are, the %4D and the %3D, as you can read about in the documentation for printf, and it's going to put that into the buffer variable. And then we're going to print line the buffer variable, and then we're going to do the LED write. So there we have it. That's the complete program, and we're not going to be able to compile right now because we're still downloading the support for this board. I wrote this software on the other computer, so this is how we'll do it. We'll just go and into the board manager and download the support for the board here, and that's how you do it. There we go. Alright, it's been a little while. Had some difficulties, but got through them. Discovered that although the manufacturer implies that you shouldn't have to, I had to put the chip into bootloader mode in order to load a program.
Alright, this is pretty awesome. Look at this witchcraft. I figured out how to split my screen. Alright, so we've got on the left hand side of the video, we've got the Arduino environment with the serial monitor open. And on the left hand here, over here, you can see the numbers flying by. The first column is the potentiometer reading, and the output is the, let me make this bigger. The output is the, or the second column rather, is the PWM value that's being written. Now over here, as I turn this potentiometer, these numbers over here are going to go, this column is going to start increasing. See, it's pretty close to 0. And now I'm going to turn this. Oops. The screwdriver slides right out of that tiny little slot. Okay, so now we're up around 20. We're going to go all the way to 3,000. 50, 60, 70. Oops, let me show you the LED as we do this. Okay, we're getting some brightness. See, the PWM output is at 3. So now we can go down and turn it off. And then as we crank it up, see, oh, it's on. See that LED over there? Yep, it's on. So now, turn it up, up, up. It's getting brighter and brighter. Oh, look at that beautiful baby glowing. She's a glowing. And so we've got the PW or the potentiometer is being read at 630 or so out of about 3,000, and the PWM value is 50 out of 255. So let's crank it all the way up and watch it get brighter and brighter until the PWM value is 255. That'll be the max. So now it's about 100. We'll keep going. The reading is at 1500 now, halfway. Output should be around 127, that's halfway. Okay. Brighter and brighter. Oh yeah, look at that. Okay. 2000, 22, 2300, and output is 200 or so. Oh geez. Okay, here we go. All right. 2700. 2850. Dang it. Maybe I need a bigger size screwdriver. Okay. And there's the maximum. That's as bright as it gets now. Well, I mean, that's not as bright as it gets, but it's as bright as it's going to get here with this resistor. We could put in a lower ohm resistor and get some more out of it. Now we'll turn it down and watch it fade out. Dun, 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 na, 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 na. All right. That was incredible. Incredible. All right, pizza lovers. It's been real. Thanks for watching.